So we are taking a look at notebook page 19 and then notebook page 20. So looking how to solve the first two questions here, practice questions. So as I've done solving questions in the classroom, I like to annotate. So the first thing when I'm looking at a problem is, as I read through it, I like to underline any values I see and their unit, and then identify what type of variable they represent. So degree C means it's a temperature. So both of these are a temperature. And when I read through this, it says going from this temperature to this one. So where I'm coming from would be temperature 1, and where I'm heading to would be temperature 2. And as I keep reading through this question, I notice there's a 418 with a J. And so that indicates to me that this is a Q value. And then I have a question that, so here it is, what is? So that's the question. And mass is my unknown. So when I take a look at the equation, Q equals M times C times delta T, and I look at what I have available to me. Well, I have the Q value, I have delta T information, I know that the M, mass, is my unknown, so I must also know the C, the specific heat value. And when I go back into the problem, I notice the word water, and so water's specific heat value is on table B in our chemistry reference tables. So now I just go and substitute all the known values into the problem. So where Q's position is I replace Q with 418 joules equals, M is my unknown, so I leave the variable M. You could change it into an X if that helps you solve it better. For C, when I look on table B, it is 4.18 joules per gram degrees Celsius. And then delta T, so I'm going to make a side note, delta T is only calculated as T2 minus T1. So the temperature that my water ends at is 20 degrees Celsius minus the initial or starting temperature of 10 degrees Celsius. So now I have the variables replaced with their values. Now I can pick up my calculator. So I can divide 418 by 4.18, which gives me 100. And then I need to divide it by the difference of 20 minus 10, which is 10. So I have 100 divided by 10. So the best answer here is B, 10 grams. When I look at question number 2, okay, I take a look at it and I'm pretty methodical in how I approach these. So I go through it all in the same manner. So I read through the problem, and as I'm reading it, I start to underline numbers and paying attention to the unit. So here I have a 15.1, and I see a unit of G, which stands for grams, and we measure mass in grams. I keep moving along. Next number I see is 48.75, and I see it's tagged with a joule, so that's my amount, and it says joules of heat, the amount of heat, so that is the variable Q. I keep going, and I see 25.0, and I see a degree Celsius, which means it's a temperature. So I have to ask myself, okay, is this the temperature 1 where the sample starts at? Is this the ending temperature, T2? Or am I just given how much the temperature changed by? So when I read through this, it says the temperature increases 25 degrees Celsius. So based on that reading, it is the actual delta T value. And then I see the word what. And so when I see like this what or determine, It's asking me to determine the specific heat capacity. And so that means my unknown is variable C. So I have my equation. It's still Q equals M times C times delta T. Now I'm just going to replace each variable with the provided value. So in the position of Q, I'm going to replace it with 48.75 joules equals now M's value, which is the 15.1 grams. C, this is my unknown. My preference is just to leave the variable in there. You could replace it with X and solve for X. And now I'm given just the amount of the temperature change, so I don't have to do any other calculations. So the temperature changed by 25 degrees Celsius. So now that I have my correct numerical setup, it's time to pick up the calculator. So I first put in 48.75 and I divide it by 15.1. Hit your equal button and then hit division and divide by 25.0. And so when you put this in your calculator, you're going to have an answer that shows up something like this. Right? And so now I take a look at what I see on my calculator and I come over and I take a look at the list and I choose the one that is the most similar to my calculator answer. So 0.129 is the best answer, answer A. Moving on, bottom part of page 19, we're going to look at a lab procedure that is called calorimetry. So this is a lab procedure to collect the data and then calculate the amount of heat that's transferred between two different materials. So calorimetry is a lab procedure that is used to determine the number of calories or the amount of energy in each food serving. So during the process or the lab procedure of calorimetry, we have our reactant, which is our material of interest, and then the other substance that is always used is water. This lab procedure collects the data that can fit into the Q equals MC delta T equation, and it also applies the idea of the law of conservation of energy. Energy can't disappear from the universe, but it can be forced to transfer between two materials in contact. And the big idea with this energy transfer is that the substance or material that releases energy or it has a loss of energy, so it goes through the exothermic process, it then releases or sends the energy to the substance that's willing to gain it or absorb it. So the substance that is going through the endo process. So this is the direction of that heat transfer. So here we go. If it's an exo process, the amount of heat it actually releases, we can quantify as Q, as in our Q equals MC delta T. The material that absorbs the energy, the amount of energy it absorbs, we can also quantify as Q. The difference here between these two numbers is their sign. So a material that is releasing heat, we deduct it from its total energy that's stored. A substance that is absorbing the energy, that heat, we then add that to its energy store. So the big idea is that the actual Q value, these two materials will have the exact same Q value, but the sign will tell us whether it was deducted or lost or absorbed. So we're going to look at page 20 and take a look at some lab data. So here is lab data that was collected during a simple calorimetry lab procedure. So notice in this lab, we're using some sort of metal and then water. So our one material is metal, the other one is water. So let's first take a look at the data. Ask yourself, what happened to the metal's temperature? So when I take a look here, the initial temperature of the metal is 97, and then the final temperature of the metal is 35. So its temperature went from 97 degrees Celsius to 35. So overall, there's a decrease in the temperature. Why did the metal's temperature decrease? What did the metal do with heat? Did it pull heat into its structure or release and send it out? If your temperature decreases, then that means that the metal, or when it released the heat. And if the metal released the heat, then that means it went through an exothermic process. So when we collect the lab data with temperature, mass, and if we know it's specific heat, if the temperature decreased, then on the calculator, the Q value is going to be calculated with a negative sign. When we look at the water's data that was collected, okay, the water, its initial or starting temperature is 23. And by the end of the lab experiment, the water's temperature, so final temperature of the water, is 35. So what happened here is that overall during the procedure, the water's temperature increased. Why did the temperature increase? What did the water do with heat? It either absorbed it or released it. The water's temperature will only increase if it absorbs enough heat. So the water absorbs. So if we describe water as absorbing heat, then that means that the water went through an endothermic process. So if our temperature overall increases, then we are going to have a positive Q value. So once again, write yourself a note. If the water and the metal are used in this calorimetry lab together, the Q value, the actual digits that make up the number of joules of the metal, and the digits or the value of the water's Q, these are going to be the exact same value. It's just that the metal is negative because it sent energy out of its structure, and the water is positive. So at the beginning of this unit, you guys learned that the heat flow, so if I make a little another note here, heat flow is always from the warmer material to the cooler material. So if I have, this is supposed to be my metal, the metal starts off at a temperature of 97 degrees Celsius. And then I've got my container of water, right? So here's the water. And at some point in the lab, the metal and the water are going to be in contact with each other. And the water's starting temperature is 23 degrees Celsius. So the metal being warmer, it is going to transfer heat. The metal will transfer heat to the water because the metal has a higher temperature than the water. So in this case, okay, if we take and look at it, the number of joules of heat, that is Q, right? Q is just the quantifying the actual number of joules of heat. And for the metal, because the metal is getting rid of it, this Q value is going to be negative. But because the water is accepting and taking it in, that Q value for the water is going to be positive, as a way to think through it. Okay, so now we have this lab data and we have some calculations to make for it. So the first thing that we are asked to do is to calculate the mass of the water. So when you take a look up here in the data table, there is not a line of data that specifically says mass of water. Like here's the mass of the metal, so that number there only belongs to the metal. But we don't have that. We have a line here that says mass of the calorimetry cup and the water. So this number here belongs to both the water and the calorimetry cup. So that would be something that we would refer to as a combined mass. So we talked about that earlier in the year, combined mass. So we have to come up with the water's mass. So it would be our combined mass of 240.3 grams, because it's asking us to show the work. That means correct numerical setup. Minus, so this is the combined, we need to remove from it the mass of the calorimetry cup, which is 59.8 grams, and that's the container. So that's the calorimetry cup. So when you put this number and do this math in the calculator, you end up with a difference of 180.5 grams. This is the mass of the water in the cup. So that's the mass of the H2O. So now we know the mass of the water. Moving to the next one, it says calculate the Q of the water. So here we have this term calculate. This is our job. That's our unknown, and it points it right up, variable Q. So take a look here. We only have one equation at this point that's a Q. So this must be a Q equals M times C times delta T. Now, the one thing I want to point out is when you look at your data table, in this data table, there is information about the metal when you look all the way through, and then there is information about the water. In this particular problem, it's asking us to do something for the water, calculate the Q of the water. So that means that when you replace the variable M with a mass, it is the mass of the water. When you replace the variable C with the specific heat value, it needs to be the specific heat value of the water. And when you put in your information for the delta T, it's the temperature change that the water went through. So don't go too fast and just grab any numbers from here. Make sure the numbers that you grab belong to the water for this question. So Q is my unknown. So now I need to know the mass of the water. And when you look at the data table, there's no line in the data table that specifically says mass of water. That's why we did calculation number 1. So this is the mass of the water that we use. So we're going to put in 180.5 grams. This is water, specific heat. You know that you find that on your table B of your reference tables. So the specific heat value for water is 4.18 joules per gram degrees Celsius. Now delta T. So little side note, you know that when you're doing correct numerical setup, don't do any intermediate math. So delta T is always T2 minus T1. So we're going to put this type of information to get our correct numerical setup 100% correct, no intermediate math. So the temperatures, final temperature where it ended was 35 degrees Celsius minus the temperature it started at, which was 23 degrees Celsius. Those are listed in the data table up above. So now it's pretty simple math in your calculator. So 180.5 times 4.18 times, open parentheses, 35 minus 23, close parentheses, hit your equal button. And I'm just going to write down the digits that show up. So 9,053.88 joules. Okay. Moving on to question 3. Now look at this. In question 3, is it asking you to calculate or determine? It says list the Q of the metal. It just simply says to list. So in question 3, there is no math involved. To answer number 3, it's taking in those ideas. So take a look here. What we showed before is that the transfer went from the metal to the water, right? Well, on this line, we can put the actual Q value because the metal is releasing those number of joules. It's negative. The water is absorbing it, so it's positive. And so we know how much heat the water absorbed there. And where did it get it from? It got it from the metal. So we know that the Q here is 9,053.88 joules. And because it's the metal, and the metal got rid of it, that number of joules, we show it as a negative number. So it's the same value, just opposite sign. So now take a look. We're getting down to our last calculation here. So when we're reading it, it says calculate. So calculate, that means we've got to come up with something. We're asked to come up with C. We only have one equation that we use that has a variable C that stands for specific heat. The same one. So it's Q equals M times C times delta T. But when we read this, we need to calculate the C of the metal. Okay, so we have to calculate the C of the metal. So that means we need to know the Q of the metal. We need to know the mass of the metal. The C has to belong to the metal, not to the water. And the temperature change has to belong to the metal also. So we only can put in information about the metal. So I'm going to put in, oh, and the unknown happens to be the specific heat. So that means I know the delta T, I know the mass, and I know the Q of the metal. So the Q of the metal, you have to keep this. It's a negative sign. So it's negative 9,053.88 joules equals the mass of the metal. It's not the same. It's not this. This is the mass of the water. We've got to go back up to the data table. Look at here in the data table. Mass of the metal, it's 379.4. So that's the mass I put in. 379.4 grams. The specific heat is my unknown, so I'll just put it in as C. And then delta T, we just always put it in. For correct numerical setup, we show it T2 minus T1. So the metal's temperature, final temperature, ended up being 35 degrees Celsius. So T2 is 35 degrees Celsius minus T1. Where did the metal's temperature start at? It started at 97 degrees Celsius. So it's 35 degrees Celsius minus 97 degrees Celsius. But take a look. The temperature decrease, so 35 minus 97 is a negative value. But you also have a negative Q value. So a negative Q divided by a negative delta T, you end up with a positive number. So when you put this into the calculator, the specific heat value calculates out to 0.38 joules per gram degrees Celsius. So in order to come up with the identity of the metal, you take your answer and then you compare it to a known list. And so the list, the one in the list that this best matches would be copper. So we are going to say The unknown metal used in this lab was copper.